Okay, so a moment of inertia. We're talking about area moment of inertia, right? Area moment of inertia of the area. Oh, there you go. Of the area shown. And read this carefully. Sometimes I might ask for x and y. Sometimes maybe just x if I'm trying to shorten the problem. So this time I'm wanting the ix and the iy. So I'm going to take this. It's a composite body. I'm going to break this up into shapes. So I've got one rectangle, two rectangles, three rectangles. So I'm going to take each one of those. Ix is the equation that I'm given plus AD squared. Use the parallel axis theorem for all of those rectangles. I'm going to do the same thing for IY, AD squared. All right. Now, we're lucky. These are all rectangles. Look for circles. Look at triangles. And rectangles. I think that's all I'm going to give you. I'm not going to give you quarter circles or half circles. But I'm not going to give you arcs. But definitely triangles and circles and rectangles. Okay, so let's do IX. IX. All right, so for rectangle number one, the IX, and we have a formula sheet that's got some I's here. IX is, but I think you should know, for rectangles, 1/12 BH cubed, right? 1/12 BH cubed. So this would be 1/12 B H cubed, all right? But that is the I about the centroid of that shape. I want the I about this x axis, so I need to use the parallel axis theorem. I need to move it AD squared. So first of all, what is the A? Well, it's always going to be this, the base times height, right? Area is base times height. And what distance do I need to move it? Okay. Let me see here. This middle part is 300, so this is 150 from here to here. And then another 25, so correct me if I'm wrong, 175. Don't forget to square that. If I was keeping up with my units, that might help me remember to square it. This is millimeters, 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 millimeters. My answer is millimeters to the fourth, right? So that would help me to square that. Okay, let's do the middle one. 1/12. B H cubed. That is the I about the middle of the middle one. And you know what? That is the axis I wanted it on. That there is no AD squared for this one because it's already about the axis that I was interested in. Awesome. Awesome. Great. All right. And then this bottom one, 1/12 B H cubed plus area base times height. And then what distance do I need to move it? It is the same. Let's see, 150 and another 25, 175 squared. All right. 175 squared. If it is symmetric, I could have just multiplied that times 2 and not done this last one. Don't take too many shortcuts if you're not comfortable with it. You can just do it this way, the way that I did this. So this is IX would be 7.29 times 10 to the 8 millimeters to the fourth. 7.29 times 10 to the 8 millimeters to the fourth. Okay, so one thing here, be able to do composite bodies where you have a shape that is cut out, right? Where you have a shape that is a hole, right? You would just subtract, if something was cut out, you would subtract its I and AD squared. So this one, I actually could have said, instead of this being an I could have said, well, this is a large rectangle, and I could subtract out these two rectangles. I would get the same IX. That one might have been easier because I don't think I would have to use the parallel axis theorem because all three of those rectangles, the middle is about the axis I was interested in. That probably would have been quicker and easier if you had seen that. All right. Sometimes you have different methods to get to the same answer. All right, let's do IY. Let's do IY. IY, there's a formula, but it's 1/12 hb cubed. We really just switch these heights and bases, right? 1/12 hb cubed. All right, so that is the I. So here's shape 1. That is the I about that, which is the axis that I want. That is my y-axis, right? That right there is the y-axis that I want to calculate my moment of inertia about, so I don't have to move it. I don't have to move it. What about that middle one? 1/12 hb cubed. Same thing. That's the I about the middle, and that's the y-axis. And then the bottom one, 1/12 hb cubed. Again, I didn't have to move it. That won't happen all the times, but if it is symmetric about the y-axis, that might happen. Don't try to make it more complicated than it is. Don't try to add AD squared if you don't have to. 6.98 times 10 to the 7 millimeters to the 4th. Now, does that make sense that your IX was larger than my IY? Does it make sense that my IX was larger than my IY? I is a measure of how much area and how far away from the axis it is. Yeah, look at this y-axis. Look at this y-axis. You know, it doesn't get too far away from the y-axis, you know, as opposed to my x-axis. And look, I've got all this area that's, you know, 150 to 200 away from my x-axis. So yeah, I think you many times should be able to tell which one should be larger than the other. And it really just means that it would be harder to bend this beam about the x-axis than the y-axis. Imagine this is very large, almost like a ruler. How about an I-shaped ruler? It's easier to bend the ruler about this y-axis than the x-axis. Well, it's really to column buckling, if you think about it. But well, it's really stress. Yeah. Okay. Don't worry too much about that. Okay. So moment of inertia about a composite body, about an area that's made up of rectangles, triangles, circles, maybe solid objects with other objects cut out of it. Be ready for this problem.